Let's begin. Welcome everybody. Your next homework assignment still isn't due for a while. You've got a week until that assignment needs to be submitted. I've already gotten some questions via email for the assignment, so it's good that you're getting an early start looking at it. As a reminder for this afternoon's lab, at 2 o'clock A through J and at 3 o'clock K through Z. And if you saw the email I sent earlier, it would be great if you're able to bring a laptop computer to today's lab, and specifically a Windows computer. We're going to be using EPANet during today's lab, and it's free software that you can obtain directly from the EPA. And if you don't have access to your own Windows laptop, you can run the software on one of the lab computers on campus. And you don't even have to install the software. As I'll show you, there's a non-installing version, which means basically you can run the program and not have to have the administrative rights to install software on the machine that you use. So we'll go over that in today's lab. Today we're going to continue some of the concepts that were introduced last Tuesday in lab, where we did that hydrostatic force experiment. So today we'll get into a lot more depth and detail, and just because proficiency at solving these types of problems is a matter of repetition, we're going to go through several. I think I've got 4 examples that we'll tackle in today's class. And my hope is that after going through these examples, then you'll have enough experience that the homework will be that much easier for you to start to work on. Any questions before we start talking about hydrostatic forces? Okay, here's an illustration of what you're going to need when we start substituting in the area moment of inertia into these calculations with hydrostatic forces. And it's the area moment of inertia about the horizontal axis that you have to know for a certain shape in order to find the location of a submerged hydrostatic force. And so just to set the groundwork, I know maybe this is a little bit hard to read if it's small on the screen, but the area moment of inertia for a rectangle is AB cubed divided by 12, where A is the width of some submerged body and B is the height. And it doesn't matter if it's perfectly vertically oriented or if it's inclined. The horizontal component would be A, which is just to the first power, and then that vertical distance would be what is cubed. So AB cubed divided by 12 for a rectangle. There are a few other shapes that we'll see besides rectangle. Circle is the most common, and the area moment of inertia for a circle is just pi times the radius to the 4th divided by 4. Now, it shows the centroid, which is the center of area for each of these shapes. And that's another thing that we're going to be talking about today is the center of area, because if we can identify the location of the center of area, that enables us to determine the pressure that applies when determining when calculating the hydrostatic force magnitude. All right. So consider that we have some body of water and it's being held back with a gate that could rotate about a hinge. So just try and visualize that maybe this is some sort of a concrete wall. Could be a dam of some sort. And at the top is a gate that can hinge open and water will spill out if that gate hinges open and rotates. Above the water is air. And you can see from the dimensions that are provided here, it's 4 meters from the top edge of this concrete wall to the hinge point, and then there's a meter of air above that to the top of the gate. Now, in problems like this, which you'll most likely see on the FE exam if you happen to take that later on, there are plenty of these fluid statics problems on the FE because they're the kind of thing that you can solve in 3 or 4 minutes. And that's what the FE is sort of tuned towards, is problems that you can solve in a relatively short period of time. So hydrostatic forces problems are important just for that reason alone. Usually, to know really what's happening, you'd have to have another view as well, or be given a description that tells you the width of the gate. So this is just telling us the height of the gate, but we don't know how wide the gate is. And the magnitude of the force is going to depend on, the absolute size of the gate. And so if we had a front view, this front view would define the width parameter A. So you can see, just going back to the area moment of inertia formulas from the previous slide, I've identified B as being the distance from the water line down to the location where the water is in contact with the gate. But it does not include that small overlapping section of the gate that was in contact with the concrete. It's just where the water is pressing on the gate. So that's going to have an influence on the magnitude of the force and also its location. So A is the width, B is the distance from the water line down to where the water is applied. So how hard is the water pushing on the gate? And that's kind of a non-technical way to ask it. How hard is the water pushing on the gate? Maybe more precisely, what we would need to determine is what's the magnitude of the equivalent hydrostatic force? Because what's really happening here is that there's pressure acting on the gate. So pressure over an area is a force. So it's not that there's one single hydrostatic force acting at a point, but really it's a distributed pressure that's acting over an area. And sometimes it's convenient for us to represent that distributed pressure as a point force, like when we're doing moment analysis or other calculations. So what's really happening is the water has a linearly increasing pressure that's acting on the gate. So the slope of this line is related to the unit weight of the fluid. So remember, the rate that pressure accumulates is gamma, 9810 newtons per meter cubed. So the unit weight of water, 9810 newtons per meter cubed, is the same thing as saying that pressure increases by 9810 newtons per meter squared per meter of depth. So the slope of this line tells you how much the pressure, how quickly the pressure is increasing. If you go down a depth of 1 meter, then the pressure at that depth of 1 meter is 9810. You go down another meter, the pressure is increased by another 9810. And so this increasing linear pressure distribution, what we'll want to do in problems like this is integrate that increasing pressure over the area of the gate and find an equivalent hydrostatic force. So remember, force is pressure times area. If we think about the units, pressure is newtons per meter squared. Area is units of meters. So that will give us units of newtons on the left-hand side of the equation, and that's kind of what we'd expect for if we're quantifying the force. And so we want to know what is the equivalent force. So if you were going to take the effect of this pressure distribution acting over the gate and just represent it by a single point force, how big would that force be and at what location? So that's the sort of thing that we're going to develop a process for determining. There's a calculation procedure that we can use to calculate the magnitude of the force and how deep beneath the surface that force is located. Any questions so far? Now, make note of the centroid. The centroid is the center of area. And specifically, it's not the center of area of the entire gate, but it's the center of area of the submerged portion of the gate that the water is acting on. So this little red dot here is meant to be the midpoint between the hinge and where the water stops contacting the gate. So halfway up from the bottom to the top, or halfway from the top down towards the bottom is where that center of area is located. Side to side, since this is a rectangle, it's just in the middle, side to side. But then vertically we have to look at what is this dimension B. And so 1/2 of B would locate the centroid for us. All right. Now, this was if the water was all the way up to the top of the gate. In other words, the gate is not submerged beneath the water surface, but the gate is either right at the top of the water or sticking out. And it has this triangular distribution. The force is located 2/3 of the way down in this triangular distribution, because if you look at what's the center of area of a triangle, it's 1/3 of the way up from the bottom base or 2/3 of the way down from the top. Now that only applies in this specific case where the pressure starts at 0 at the top edge of the gate. But more often these gates would be fully submerged. And so now think about, here's a gate that has a width of A, a height of B, and the gate is beneath the water line. This dashed blue line here just represents the surface of the water. So it's beneath the water. This pressure distribution started at 0 and increased linearly. But at the top edge of this gate, the pressure doesn't start at 0 because it's already beneath the water surface. So the pressure starts at some non-zero magnitude and acts increasing as you go downward with the depth. So finding the location of the equivalent hydrostatic force isn't just as easy as saying it's 1/3 of the way down the gate. That only applies if the gate was up to the top of the water surface. So we have to have a more generalizable approach to finding the location of the hydrostatic force. So here's that hydrostatic force, the equivalent force that is integrating a pressure over an area. And to find the magnitude of the force, so the force magnitude is pressure at the centroid multiplied by the area. So if we know the pressure at this centroid location, P bar is how we'll denote the pressure at the centroid, we can find the magnitude of the force. Usually the magnitude of the force is relatively easy to determine because finding the depth to the centroid isn't so tricky. But finding the location of the force is a little more involved. As I'll show you, the equations for that are just slightly more complicated than P bar times A. What happens when you start to submerge this gate, the location of the force starts to get closer to the centroid. And if you submerge it really deep, so like 100 meters under the surface, then that force location is very close to the centroid because there's not as much, on a relative basis, there's not as much difference in pressure between the top side of the gate and the bottom side of the gate. You know, in this case, the top of the gate and the bottom of the gate have a very different pressure. The top of the gate is 0. The bottom of the gate is some maximum point. And so there's a big distribution between the pressure at the top and the pressure at the bottom. And so that drives the location of the force further below the centroid than will be the case when the gate is all the way submerged, like here. So the deeper submerged it is, the force gets closer to the centroid. But you can calculate the precise location of that force. Now let's consider the case of a fully submerged gate, and this time it's inclined. The previous illustration, it was vertically oriented, but we need to have formulas that will work for us if the gate's fully submerged and if it's not straight up and down. Straight up and down is too simple. We need something that will help us to find the magnitude and the location of the force even when the gate is sideways. So that's what this is. Think of this as a tank of water. Delta H is obviously the depth from the water surface down to the centroid. So this red dot, again, is just representing the middle point of the center of area of the gate. So we're looking at this from a side view. So we don't necessarily know the width of the gate from this side view. But from the side view, we do know the height of the gate. And the red dot is halfway between the top and the bottom. So it's in the middle, vertically. F is the magnitude of the equivalent hydrostatic force. And you'll notice that F is at an angle as well. Because the gate is tilted, the force is normal to the surface of the gate. All right, so delta H is the depth to the centroid. And specifically, it's the vertical depth to the centroid. So going straight down from the water surface to the center of area. That's H bar. Y bar is the inclined distance from the water surface to the centroid. So Y bar follows a path at the same angle as the gate, whereas delta H was straight up, Y bar is at an angle. YCP is the inclined distance from the force location to the water surface, and it follows the same angle that Y bar did. But YCP, CP stands for center of pressure, because the center of area is this red dot, but the equivalent hydrostatic force is located at the center of pressure that is acting on the gate. So if you want to find out where that force is applied, you have to calculate YCP, the inclined distance from the water surface to the center of pressure. And then there's a formula for YCP, and once you calculate it, that will help you to identify where the force is applied. Any questions so far? All right, so let's review these terms. Delta H is the vertical distance from the centroid to the water surface. And when you know that vertical distance, that's how you find P bar. So P bar, the pressure at the centroid, is determined by delta H. So in other words, the force magnitude, F, is delta H times gamma times A. That's how you find the magnitude of the hydrostatic force, is by knowing delta H. The pressure at the centroid, delta H times gamma. Y bar is the inclined distance from the water surface to the centroid. So if we, in this image, follow the red dot up to the surface, then it would be from the red dot to the water level. Then YCP is a little bit below the red dot, because that's where the force is applied. So it's the inclined distance from the water surface to the center of pressure. And I'll show you in just the next slide the formula for YCP. The center of pressure is where the equivalent hydrostatic force is located, and it's going to generally be below the center of area for the gate. Okay, here's the formula for YCP, and it utilizes the depth to the centroid along the slant route, so Y bar. It also utilizes the area moment of inertia in the numerator, and then the area of the gate is one of the components in the denominator. So this is how we can calculate YCP. If we want to know how far below the water surface along that inclined path we have to go to the force location, then we have to know Y bar, area moment of inertia, and the area. Now, if we subtract Y bar from both sides of the equation, YCP minus Y bar, what you can think of that as, it's the distance between this red dot and where the force is located. And let me tell you why that's significant. Let me just briefly go back to this slide. All right, you can see that the force is located below this center of area. If there's a pin or a pivot point here, then it potentially could cause this to spin, like if it was at the outside of the tank acting as a gate. This gate could spin. And so we may need to know, like, what's the moment or the tendency for that to rotate counterclockwise. So it would be the force times some distance. And the distance between where the force is applied and their center of area, that distance is YCP minus Y bar. So Y bar is from the surface to the center of area. YCP is from the surface to the force location. And so this gap distance, I should make that even more obvious. Let me see if I can insert a shape that looks like this. Rotate it. Now, that kind of makes it clear. All right, so this, almost had it. Boy, it's really tricky. All right, well, I hope you get the idea that this is the gap distance that is YCP minus Y bar. YCP minus Y bar is that distance. Okay, now let's go back to this example problem type. And let's go through the process of finding a couple of things here. We want to find the magnitude and location of the hydrostatic force. So let me write this up on the board. All right. So we have a gate that is 3 meters in width. So 3 meters in width, and the relevant height that the water is applying to B is 4 meters. Okay, and this width is the parameter A. The unit weight of the fluid is 9790 based on the temperature of the water in this example. And the first thing we're going to do, step 1, is find the distance to the centroid. So find delta H, the depth to the centroid. So here's the centroid, and just by inspection, we can see that the depth to the centroid is going to be, since it's 4 meters from the top to the bottom of the gate, it would be half of that. So it's simply going to be B divided by 2 in this case. And so it's 2 meters is the distance, delta H, from the water surface down to where the center of area of that gate is located. Okay, so delta H is 2 meters. Next step, part 2, let's find the pressure at the centroid, P bar. And we know pressure at the centroid is delta H times gamma. Okay, so that's 2 meters of depth and 9790 newtons per meter cubed. So the pressure at that location is 19,580 pascals. Okay, so we've got the pressure at that depth. All right. 3, find the magnitude of the hydrostatic force. So the force is P bar times area. So the magnitude of the hydrostatic force is going to be 19,580 newtons per meter squared times the area. And the area is 3 meters times 4 meters. So it's 12 square meters is the area of that gate. So then the pressure at the centroid multiplied by the area gives us 234,960 newtons. Okay, so that's the magnitude of the force. Now finally, the trickiest part is finding the location of the force. So force location. What we already had was that delta H is 2 meters. So delta H is 2 meters. And since the gate is vertically oriented in this example, Y bar is also 2 meters because it's straight up and down. Remember, Y bar would ordinarily be the slant distance from the center of area to the water surface. But since it's vertically oriented, delta H equals Y bar. The area moment of inertia, I, is AB cubed divided by 12. So it's 3 meters times 4 meters cubed divided by 12. So that's 16 meters to the 4th is the area moment of inertia. And now we'll use the formula for YCP. So YCP is Y bar plus I divided by Y bar A. All right, so that's 2 meters plus 16 meters to the 4th divided by 2 meters times the area of 12 meters squared. And that is 2.667 meters. So that means that the force is located 2.667 meters down. So this is where the force would be applied. Now, let's go back to the example briefly. Because there's one more part of this. There's a moment analysis that we have to do. Okay, so what we've just determined is the magnitude and the location of the force of the water acting on this gate. So that's causing the gate to rotate counterclockwise, unless it's resisted by this force F. So this force F, which is pushing in a clockwise direction, is meant to ensure that the gate is in equilibrium and that it doesn't rotate and the water doesn't spill out. Okay, so we know the magnitude of the force. Let me just to draw that in real quick. So we've just determined that there's some force acting over here. Okay, so here's some force, and the magnitude is 234,960, and the location is 2.667 meters down from the hinge point. And we want to know what force F is required to hold the system steady. so that the gate doesn't open and the water doesn't spill out. Okay, so the last part of this problem then is that we, let me just show you because I've got it right here. Here's the water line. That dashed line represents the water. 2.667 meters down is this hydrostatic force acting in the counterclockwise direction. The magnitude of it is 234,960. And then F has a moment distance of 4 meters. So that's the distance vertically down from the pivot point. Here's this hinge. And so it's going to be some force acting at 4 meters is resisting this known force of 234,960 acting at a distance of 2.667 meters. So we multiply the force times the distance for the counterclockwise rotation. And here on the right-hand side of the equation is the force that's resisting that times the distance of 4 meters. And you can see that when we do the calculation that F, the force required to hold it steady, is 156 kilonewtons. All right, so did everybody follow through that? Is there any question on a certain thing that didn't seem immediately obvious or that you'd like to have clarified? Okay, so the steps are, number 1, find the depth to the centroid. Number 2, find the pressure at the centroid. Number 3, find the magnitude of the hydrostatic force. Number 4, find the location of the force. And then in problems like this, sometimes that'll be it. In other cases, you'll have to do some sort of a moment balance to find out like a force required to open a gate or to keep a gate closed and so on. So we can apply that same technique in other situations, such as this one. So what I'm going to do is pause for a moment and give you a time to think about the dimensions that are described and try and visualize. You know, if you have the notes printed out, draw right on the sketch. Try and locate where's the center of area. You know, I've had that as that red dot in previous drawings. So where would the red dot go here? So what we ultimately want to know is what's the force, what's the magnitude and the location of the hydrostatic force acting on the gate. So you're not going to have to do like a moment analysis on this one. It's just where is the hydrostatic force and what is its magnitude. All right, so I'll pause for a moment. I'm going to stop the recording. I'll circulate around with the answer. And I'd really be delighted if you collaborate with your classmates on this one. Try and set it up together, talk through it, and try and find out what's the force and what's the location. So you're going to have to calculate the YCP, but notice the gate doesn't start at the water surface. This is one of those where the gate is submerged. So pay careful attention to the dimensions. All right, so where have I got this one? There it is. The dimensions are intentionally a little bit tricky on this one, where it says the gate is 3 meters tall, so from the shaft down to the bottom here is 3. 3 meters tall, 2 meters wide, and the height of the water, h, is 6 meters. So that means that it's 3 meters from this edge up to the water surface. So here in the solution, we're going to be measuring delta H is from the center of area of the gate. I've got it in blue here, this blue dot on the board. And so delta H will be half of the gate height, 1.5 meters, plus the 3 meters that it is from the water surface down to the edge of this concrete wall. So in total, it's 4.5 meters. is the distance from the water surface to the centroid of the gates, delta H. And incidentally, since this is vertically oriented, delta H equals y bar. If the gate is straight up and down, y bar equals delta H. So we'll need to know that when we put it in the formula for YCP. The pressure at the centroid is just the unit weight of the fluid multiplied by delta H. So the pressure at the centroid of the gate is 44 kPa. The magnitude of the force is multiplied the pressure at the centroid by the area of the gate. So 264 kilonewtons is the magnitude of the force. And now to find the force location, this is where we have to use the formula for YCP. And so just to set the preliminaries, the y bar is equal to delta H, and the area moment of inertia, 4.5 meters to the fourth. So when we substitute it in here, the location of the center of pressure is 0.1667 meters below, so it's a little bit below that center of area of the gate. So the gap distance between where the force is applied and our center of area is 0.1667. So from the water surface to the center of that force location is 4.667. So here's where the force is applied, and that distance is 0.1667. And that would be significant if we were going to have to apply some sort of a force to resist that rotational tendency. All right, so any questions on these calculations? We're just going to make this increasingly complicated. So now you've done one that was vertically oriented and at the water surface. You've done one, so that was this first example, vertically oriented and at the water surface. This example was vertically oriented but beneath the water surface. Now we're going to do one that's inclined. So what makes this tricky is you're going to have to kind of dust off some of your memory of geometry, maybe even a little bit of trig. It's probably been a while since you did that, but you'll need it to find things like, you know, what's the depth to the centroid? What's the inclined distance, and how does that all apply? Okay, so here we've got a rectangular plate. So you can see from the front view it's 2 meters wide. From the side view you can see it's 3 meter height dimension. And it's oriented at a 45-degree angle. Okay, now even though it's vertically oriented like this, we still use the full 3 meter height as B. So A is 2 meters and B is 3 meters. It doesn't matter that it's tipped over. It doesn't change the dimensions of A and B. We're going to go through this similar process. We'll find the depth to the centroid, so delta H. We'll calculate the magnitude of the force. Now we know the magnitude of the force is the pressure at the centroid times the area. So we'll skip the intermediate step of calculating the pressure at the centroid separately. Okay, so find the magnitude of the force, determine the area moment of inertia, and the location of the force. All right, so let me do this one on the whiteboard. I'm curious to know how many of you have the notes printed out. Like when I turn off the screen, are you still able to look at this, or should I maybe copy it onto the board? Because it looks like some of you don't have the notes printed. So I'll do that. I'll copy it onto the board. Basically, all we need to remember is that it is, here's the water surface, our gate, our plate, this edge is 5 meters down. So it's 5 meters vertical distance to the top edge of the gate. And it's at an angle of 45 degrees. Okay. Okay, first thing we want to find is the depth to the centroid, delta H. Now, this is where we have to do a little bit of geometry. And what we're looking for is the distance from the center of the plate's area, so from the centroid up to the water surface. And so this, oh, that's not even a vertical line. That's a little more like it. Delta H. So it's not 5 meters, right? 5 meters is from the top edge of that plate. I want to know delta H to the center of the plate's area. So it's going to be 5 meters plus this distance, plus a little more. Okay, so that is going to be delta H is 5 meters plus 1.5 meters, because remember it's this dimension is 3 meters. Okay, so half of that is 1.5. But I can't just say 1.5 by itself, because that's like a sideways distance. I want to know the vertical component of this sideways distance. And so for that, what I'll say is times the sine of 45 degrees. So that'll give me the vertical component of this inclined distance. And the sine of 45 degrees is 0.7071. And so the overall delta H is 6.061 meters. Okay, so it's obviously got to be, let me go, well, 5 meters and a little more. But it's just the vertical component of this distance from the top edge to the center of area. It's not the inclined distance we want, it's the vertical distance. And so that's why we took into account the angle of its rotation being 45 degrees. Okay, so that's part one, determining the delta H. Part two of this example said, find the magnitude of the force. So the force magnitude, F, is P bar times area, which is the same thing as saying delta H times gamma times the area. Okay, so 6.061 meters multiplied by the unit weight of water. And in this one, it doesn't tell us any particular temperature of water, so we'll just use the default unit weight assumption of 9810 newtons per meter cubed. And now the area of the gate is 2 by 3. So this plate that's under the water has a 6 meter squared cross-sectional area. So if we multiply those terms together, it's a magnitude of 356.7 kilonewtons is the magnitude of the force. All right, so any questions so far? When this is fully submerged and at an angle. Okay, step 3 was find the area moment of inertia. So I is AB cubed divided by 12. And we still use its physical dimensions even though it's inclined. And so A is the width of the gate, meaning 2 meters. B was the height of the gate, being 3 meters. And that is cubed divided by 12. So 4.5 meters to the fourth. All right. Now, the last part is the location of the force. And this gets a little bit tricky. And let's think about what we know. Put the mask on so I can write this on the other whiteboard. Here's the water. We've got this inclined plate. And what we determined so far was that the vertical distance to the center is 6.061 meters. That was the delta H. And now what we want to know is what is the YCP? I'm sorry, that's Y bar. So Y bar is from the center of area to the water surface. And so if we go up here, Y bar is the distance from the center of area to the water surface. So if it's basically a triangle, this is a triangle where we have 6.061. We want to know Y bar. And here this angle is 45 degrees. Okay, so Y bar is 6.061 meters divided by the sine of 45. And that gives us 8.572 meters. So that is the hypotenuse distance there. And now YCP is going to utilize that Y bar. So the formula for YCP is Y bar plus area moment of inertia divided by Y bar A. 8.572 meters plus 4.5 meters to the fourth divided by 8.572 meters multiplied by the area of this submerged plate, 6 meters squared. And this second term here is 0.087 meters. So the overall YCP is 8.659 meters. All right. You may have to go to Khan Academy and refresh your memory of how to use some of these geometric functions. It'll come back to you. It's been ages since you used it probably, but it'll come right back like it's yesterday. Any questions on this example where we were calculating the force, location, and magnitude for an inclined plate? It seems like things are getting complicated, right? But hey, at least the plates are flat. It gets even more kind of difficult when it's a curved plate. So we'll get there. But for now, phase 3 was a submerged inclined plate. All right, for just the one last example we're going to go through today, let's have, again, a plate that's at an angle. And this is covering the opening of a pipe. Basically, we have a tank of water and an outlet pipe that is covered with an elliptical gate. And the reason why this gate is elliptical in shape is because the pipe itself is circular in profile, but if you cut a circular pipe at an angle, then the physical opening of that cut pipe will have an elliptical shape. So just think of it maybe in 3 dimensions. This piece of paper that I'm holding is a circular pipe, and if you cut that circular pipe at an angle, then the opening is going to be an elliptical shape. And so we've essentially made some gate that is meant to cover this opening, and we're just trying to figure out here what force would be required to open up that gate. Because right now the water is keeping it closed. The pressure that's acting on the gate is forcing it closed. It's creating a moment that goes in the counterclockwise direction. So how hard would this force F need to be in order to begin opening the gate? Now, it was in that first slide for today, but here it is again. The area for an ellipse is pi AB, and A is just half of the width of the ellipse, and B is just half of the height of the ellipse. And so A and B mean slightly different things in this context than it did for a rectangle, where for a rectangle it was the entire physical height that was B, and it was the entire physical width that was A. Here it's just half of that distance for an ellipse. And we also have the area moment of inertia formula for the ellipse. All right. So what I'd like you to do is find the force of the water that's acting on the gate and the inclined distance to the center of pressure. That's the YCP distance here. And we're going to use all of that to determine the force required to open the gate. And this is one of those examples where it's easiest if you can measure things from the hinge. Ultimately, to do the moment analysis, it's about the hinge. But let me pause for a second and let you have some time to think and start to calculate how would you find the hydrostatic force. And so, it's not pictured, but the hydrostatic force, let me just sketch it out here in PowerPoint. There's this force that's acting on it. All right. It's going to be a little bit below the center of area. So here's like the centroid of the gate, right, in the physical middle. But this is going to be, this force location is a little bit lower. So the water is pressing the gate closed. We want to open up the gate. So how big does F need to be? So what you're going to need to do is, following the similar process that we've done before, you need to find out what is delta H. First of all, just draw a little dot in your sketch to indicate where's the center of area for that gate. And then the dimensions that's given here in the drawing is that, see how this says it's 8 meters. That 8-meter distance is just from the water surface to the hinge. So that's not, delta H isn't 8 meters. Delta H is going to be 8 meters plus a little bit more. And let me just draw your attention to one other thing on here. See how it says that the pipe is 2 meters in diameter, and it's 5 meters is the height of this opening. So remember a 3, 4, 5 triangle? So you can use similar triangles in some of the geometry that's required for this. And since it's a 4-meter diameter gate, then that basically tells you that the center of area is 2 meters down from the hinge, vertically. So 2.5 meters is the inclined distance to the center of area, but the vertical distance downward from the hinge to the center of area is 2 meters. So that makes the delta H a little bit easier to calculate if you notice this 4-meter diameter dimension and what that means. All right, so I'm going to pause the recording, stop talking for a minute, and I'd like you to dig in on these calculations and see if you can find out magnitude of the force. All right, so the first thing that we want to do is find the magnitude of the force. Sorry. Here we go. All right, so we've got this gate that is in an angle, and the shape of the gate, if we want to go through some preliminaries here, A is 2 meters, B is 2.5, and so we've got the area defined as 15.708 square meters. And the force magnitude is going to determine on the depth to the centroid. It's going to depend on the depth of the centroid, and the depth of the centroid is the 8-meter distance from the water surface to the edge of the gate. And then if we're going down to the center of where that force is applied, what I typically have been representing as a red dot, that's vertically another 2 meters down, because the vertical component of that gate is 4 meters overall. Okay, so it's 10 meters as the depth of the centroid. The force is the pressure at the centroid times the area. So delta H times gamma times the area, and it's 1.541 meganewtons. So that's 1.5 times 10 to the 6th. Yeah, times 10 to the 6th newtons. Now, in order to determine where that force is located, it helps to look at the angles that are defined for the gate's orientation relative to the y bar. So y bar is the distance from the center of area along the inclined path up to the water surface. And it's going to have the same angle up to the water surface as the 3, 4, 5. So 5, the inclined distance is corresponding to 5. The vertical component is corresponding to 10. So the y bar, the inclined distance, will be 12.5 meters from the center of area up to the water surface. Okay, and this is one of those instances where it's useful to rearrange the equation for YCP and just find the gap distance, because the moment analysis is going to be done about this hinge. And so if you can find how much further below the center point the force is located, it just makes more sense to use the hinge as the reference for measuring distances rather than the water surface. So although YCP would tell us how far is it from the water surface down to where the force is located, it's more useful for us to figure out the distance from the hinge to where the force is located. So that distance, 0.125 meters, is how much further below the centroid the hydrostatic force is applied. And finally, it's asking what force is required to actually open the gate. And down here at the left, you can kind of see the moment analysis. We've got some unknown force acting at a distance of 5 meters from the hinge point. And then the 1.541 meganewtons that we just calculated, the hydrostatic force acting at a distance of 2.5 plus 0.125. And so the moment distance is the distance from the hinge point to the center of area plus this extra 0.125 meters. So that's why this moment distance is 2.625 meters multiplied by the magnitude of the force. And what that means is, since the applicable distance is longer, the force required to open the gate is less than the hydrostatic force that was applied to it. So it only needs to be 0.809 meganewtons to counteract this 1.541 meganewton counterclockwise force. All right, well, that's all the time we have for today. It's 12:15. Just remember that your next homework assignment is due a week from today, and then in the lab today, we're going to be going over EPA net. So I'll see you there.